The question is, could you tell us when we need to use calculus to solve a problem of a cylindrical shaft subjected to torsion? Yes, there are problems where the key quantities, including the internal torque T, the radius of the shaft R, and the relevant material property, the shear modulus, vary with distance x. In these cases, we will find that the formulas we have used so far are not strictly valid. Although the torsion formula is still valid, provided we use appropriate values for the quantities in that formula, we're going to have to use calculus to find the angle of twist. Let me first give an introduction to such problems here. In the problems we have considered so far, each segment of the shaft had a constant shear modulus, constant radius, and constant torque, right? We calculated the shear stress using the torsion formula. Tau equal T rho over J. T is the torque, rho is the radius, J is the polar moment of inertia of the cross-section, right? In this formula, T and J are constants within a given segment, right? The angle of twist of point B relative to point A would be the angle of twist of this segment AB, which is given by this formula right here, right? TL over GJ evaluated for the shaft from A to B. T is the torque, L is the length, G is the shear modulus, and J is the polar moment of inertia. Again, T, G, and J had constant values within a segment, right? Now consider the case where these key quantities T, J, and G vary with x. The torsion formula can still be used, but we recognize torsion T is now a function of x. And similarly, J, the polar moment of inertia, is also a function of x. We already know tau is a function of rho, the radius, right? And therefore, tau now is a function of both the radius rho and the distance x. The formula for the angle of twist, of course, has to be modified. While the structure of this formula is still valid, the formula itself is not valid anymore. We can only consider a differential length dx and apply this formula for that length. Let me call the angle of twist of this differential element as d phi. So d phi is the angle of twist of this point relative to the other point, the point on the other end of that little differential element. D phi is now given by this formula, t as a function of x multiplied by dx divided by g as a function of x multiplied by j as a function of x. In other words, we had to follow the calculus approach here. If you are interested in finding the angular twist of point B with respect to point A, like we normally are, I have to integrate this formula. So phi of B with respect to A would be integral of d phi with x going from 0 to L. So in a more explicit manner, we integrate this quantity with respect to x with x going from 0 to L. So you can see that most of the fundamentals are still the same, but we just have to use calculus to find the angular twist of a certain point with respect to another point. Let's do an example to illustrate the use of calculus in solving torsion problems. We have a segmented rod that is fixed at point A and subjected to a concentrated torque of 15 kilonewton meter at point B and a distributed torque between B and C of 6 kilonewton meter per meter. So this is a uniformly distributed torque. Say we are interested in finding the stresses and the angular twist like we did in some of the previous problems. The shaft has a constant radius of 50 millimeters and a constant shear modulus of 40 gigapascal throughout. Here is the free body diagram of the shaft cut out of the support at point A. TA here is the support reaction. The first step is to see if this is a statically determinate problem or indeterminate problem. We have discussed this issue a few times already, so I want you to draw your knowledge from one of those videos to see this is a statically determinate problem. Now we're going to evaluate the internal torques in the segments AB and BC. Within segment AB, you can section it anywhere you want. This is because the internal torque is constant from A to B, as this equation illustrates. But within segment BC, of course, it matters exactly where you section. So let's define the x coordinate system. I mean, you can start measuring x either from A or from B. In this particular case, since we have the distributed load only within the second segment BC, it's convenient to start x from point B. Alright, let's start with our sectioning right here within AB and consider this right side, everything starting from here all the way to point C. Since TAB is going clockwise at this point, everything summed up in the counterclockwise direction should be equal to TAB. So we have 15 kilonewton meter at this point, so that goes in as a term in that equation. And then of course we have a distributed load of 6 kilonewton meter per meter, right? So if I take that and multiply that by 2 meters, we get the resultant torque associated with this distributed load, and that will be 6 multiplied by 2, and you can see the unit wise this meter and meter cancels out to give us the torque in kilonewton meter again. So this is 12, this is 15, so we get 27 kilonewton meter for TAB. Now let's consider the sectioning at this point, and this point is taken to be at a distance x from point B. Once again, I'm going to consider the right side here. In other words, starting from this point all the way to point C. TBC then must be equal to the total external force going in the counterclockwise direction. So that will be the distributed load multiplied by this distance, right? This distance is 2 minus x. So that's what I have over here. So you get 12 minus 6x kilonewton meter for TBC. Now we see that torque within BC is a function of x. Now we use the torsion formula to calculate the shear stresses. I'm calculating the polar moment of inertia first. So we get a value of 9.813 times 10 to the minus 6 meter to the power of 4 for that. The torque is a constant within segment AB, and the maximum shear stress, which is the shear stress at the outer fiber of the shaft, is calculated to be 137.6 megapascal for that. Within the segment BC, however, the torque is a function of x, right, given by this equation, right? So here first I kept it as a function of x and simplified it in order to get this expression for the maximum shear stress within BC. Now this equation can be used to calculate the maximum shear stress at any location between B and C. As an example, if I pick the midpoint between points B and C, x would be equal to 1 meter, and the tau max within BC at that particular location works out to be 30.6 megapascal. The angle of twist of the segment AB is fairly straightforward, just like the problems we worked on in previous videos. This is because none of these quantities vary with distance, x, and therefore this formula is valid. I get a value of 4.73 degrees for that. Since the torque varies within BC, we use the integral formula to find the angular twist of the segment BC. But we do note that the quantities g and j are independent of x, so they can be pulled out of the integral. This expression then simplifies to this, and here is the torque within BC as a function of x. So we substitute this function in here, integrate this, apply the limits, where x goes from 0 to 2 meters, right? And I get this value, 1.75 degrees for the angular twist of segment BC. So here is the angular twist of point B, and here is the angular twist of point C. Note that in some other problems, your j could be a function of x. All you have to do is to keep j inside the integration sign and integrate that along with anything else that may be a function of x. So that's it. So the approach is the same. You just have to recognize which of the quantities are functions of x.